In this lecture, I'm going to walk through how to balance a redox reaction that isn't just a simple one, where we have a metal transferring a couple of electrons to another metal. So we talked about this in the previous lecture, and I want to continue that conversation, how to identify what is being oxidized and reduced. And here's another example. I have a combustion reaction, which is actually a redox reaction. I'm showing methane here reacting with oxygen to form carbon dioxide and water. And so if I was looking at this chemical equation, I would first go through and assign all of my oxidation states using that rule set we just reviewed. And then I would compare my reactants and my products for each of my elements. And so I've done that. I've gone through, and for like methane, I said, well, my highest priority is hydrogen, so that's +1. That means my carbon has to be a -4 oxidation state to balance out that +4 oxidation charge, I guess, coming from the hydrogen. So I'm now just going to compare these values. I've got a +4 for my carbon becoming, I'm sorry, a -4 for my carbon becoming a +4 in my products. My hydrogen is +1 in my reactants, and it's still +1 in my products. So there's no redox occurring with the hydrogen. And then looking at my oxygen, when it's an element, O2, it has an oxidation state of 0, and it's becoming -2. And so that 0 to -2 is an increase in negative charge or decrease in positive charge, which is showing reduction, that we're gaining electrons. And our carbon atom is increasing its positive charge. And so it's being oxidized. It's going from -4 to +8, and it's going to gain, lose electrons to do that. The carbon's actually losing 8 electrons when this happens, to go from -4 all the way up to +4. And my oxygen atom is going to gain only 2 electrons. And so the amount of charge that is lost or electrons that are lost by the carbon isn't the exact same number as the oxygen. And so to balance out this equation, we would have to look a little bit deeper, because not only do we balance the atoms on a chemical reaction equation, we also need to make sure the charge is balanced. So I'm going to show you the half reaction method for balancing redox reactions. If you try this and you really, really, really hate it, it's also sometimes called the ion electron method. I've got another method that involves setting up an algebraic expression for every single, for each reaction, and then solving smaller expressions with multiple variables for each of the individual elements within it. And I can send you a little tutorial on that if listening to this doesn't work for the way you kind of process information. But this is the method that seems to work for most people, so we'll go through it. So the way we're going to balance redox reactions is by balancing mass first and then charge. And so we're going to want to write a skeleton equation that's only the ions and molecules that are being involved in the actual reduction and oxidation, and break those up into 2 half reactions. So we can see what electrons are being gained or lost. And then once we have those broken up into half reactions, we're going to go ahead and balance each one separately and then combine them at the end to get a net ionic equation. So let's walk through one of these. And in your lecture notes, you have a summary of all of the steps as well. We're going to look at the most simple version of this too, to kind of see our overall structure. And this is a simple one, and we've already looked at this. We've looked at copper and zinc already when we, in our previous lecture, reviewed oxidation and reduction reactions. So I have a copper +2 ion combining with zinc metal in its elemental form, and it is going to form copper metal and then a zinc ion. So the first step is to break this into 2 half reactions based on what is being oxidized and what is being reduced. And so the focus here is for oxidation is on that zinc metal. It's being oxidized and it's gaining 2 electrons, losing 2 electrons. And so when we lose electrons, they're going to be on the product side. The other half reaction is the reduction half reaction. That copper ion is going to take 2 electrons. And so because it's gaining electrons, it's going to be on the reactant side. And it'll form then copper metal. So now I've been able to isolate these as two separate half reactions. I'm going to first make sure that the atoms are balanced on both sides. And looking at that, I can see that my zinc metal is the same on both sides. There's only one. And then my copper has just one on either side too. So my atoms are already balanced. So that part's done. Then I'm going to make sure my charge is balanced. And I can see that my 2 electrons that are produced by the zinc are the 2 electrons that my copper takes. And so my 2 electrons are going to be balanced on each of these half reactions. And so that's balanced too. See, it's insanely simple when we look at really simple examples. And so then I'm going to recombine these. And the important part here is that when we combine them, the 2 electrons are basically on both sides of our equation now when we combine our half reactions. And kind of going back to net ionic equations, whenever you have the same thing on both sides, you can cancel it out. And so we won't ever have electrons in our net ionic equation because we should be balancing the charge, balancing the number of electrons in our 2 half reactions so they're the same number. So that way, no matter what, they cancel out and we don't have to show a net need or loss of electrons. All right, so with that kind of basic formula, let's now make this a little bit more challenging. So we will need to balance our half reactions in either acidic conditions or basic conditions. And this is reflecting what you would actually do in a lab. You would either have a little bit of acid around in an electrolyte solution or base for a redox reaction. So we're still going to divide our equations into 2 half reactions. We're going to first balance our atoms. And when we balance our atoms, we're going to take care to avoid hydrogen and oxygen. We aren't going to balance them yet. Then we'll balance oxygen first of those 2. And we're going to balance it by adding water molecules to the side that has a deficit of oxygen atoms. Then we'll move on to balancing hydrogen atoms last. And we'll do that by adding H pluses to the side that don't have enough hydrogens. And this is where we get our acidic conditions. So that we're going to balance those hydrogens with acid, essentially. Now, after that point, we will go back to our kind of standard form, which is now looking at the net charge and balancing by adding electrons. And I'll be able to multiply a whole chemical half reaction by 1 value and have that applied to every coefficient, including the coefficient in front of my electrons. Once those are equal, then I'll add them back together and cancel out anything that's the same on both sides. Let's walk through an example. So I've got this chromate, I think it's chromate, plus iron, forming chromium metal and a different iron oxidation state. So the first step I do is I break this into my half reactions, and I can see my chromates going from my oxidation state for my chromate is, if my oxygen is a -2 and I have 7 of them, I'll have a total of -14. And so to get a -2 charge overall, I'm going to need a +12 charge total from my 2 chromate ions. And so that's going to give me a chromate of +6 oxidation state. So each of those chromium atoms is going from +6 to +3, which means it's going to be gaining electrons. And it'll be my reduction half equation. Now my iron is going from a +2 to a +3. It's losing electrons. So it's my oxidation half reaction. I'm now going to start managing these separately and balance first the atoms that aren't hydrogen and oxygen. Right away, I'm going to have to put a 2 in front of the chromium on my product side to balance out the 2 chromium atoms that are on my reactant side. And my irons are already balanced. There's just 1 atom on each side. Now I'm going to balance the oxygens in my first half reaction. I've got 7 oxygens on my reactant side for my reduction half equation and none on my product side. So that means I'm going to add 7 H2O molecules to the right side. And that's going to balance out those oxygen atoms. I have 7 and 7 now. My iron half reaction doesn't have oxygen, so I don't need to do anything. Now I need to balance out my hydrogens. So I don't have any on my reactant side in my reduction half reaction, but I have a total of 14 hydrogens on my product side. So since we're under acidic conditions, I'm going to balance with H+, and I'm going to need 14 of those on my reactant side. And now I should be balanced on my hydrogens. Again, my iron equation has nothing to balance. There's no hydrogens, so I don't have to do anything. All right. Now what I'm going to do is take a look at my total charge. I'm not going to take the charge that I looked at when I compared my oxidation numbers, because after adding 14 protons, or maybe I've added like hydroxide later when we do it under basic conditions, I'm going to look at that's going to change my charge that's in both sides of my equation. So I'm going to take the total charge on each side and compare it. So I have 14 hydrogen cations, each at a +1. So that's 14 times +1. I've got it right here. And my chromium oxygen ion has an overall -2 charge, so I'll include that. So I've got a +12 on my reactant side. Doing the same thing on my product side, those water molecules are all neutral, so they have a 0 charge. But the chromium ion is a +3 charge. So that'll be 2 times +3 to give me a +6. So now I need to balance this out so that way the charge is the same. They don't both have to be 0, they just have to be the same value. So if I have, and I'm doing this with electrons, so I'm going to add electrons to do this. If I add electrons to my product side, then this number will get smaller and be further away from matching that 12. So I'm going to add electrons to my reactant side to try to bring that value of 12 down to 6. And so I'm going to add 6 electrons. So now my total charge on my product side is +6 instead of my total charge on my reactant side is +6 instead of +12. So looking at my iron next, I'm going to balance out my charge. I've got a +2 on my reactant side and +3 on my product side. If I add an electron to my product side, then that'll bring the total charge on the products up to +2, and it'll be balanced. All right, now I've balanced mass, I've balanced charge. It's time to combine. So the first step in combining our two reactions is making sure that the number of electrons in both half reactions are the same. So I've got 6 electrons in my chromium half reaction, and I have only 1 in my iron half reaction. So to make that number the same, I'm actually going to multiply my entire iron equation by 6. And so that means my coefficient changes. I have 6 iron +2, 6 iron +3, and 6 electrons. Now I'll combine. And I'll combine by just adding everything together on my reactant side on one side of an arrow, and then everything on my product side will be on the product side of the arrow. So I line that all out, and now I can cancel anything that is the same on both sides. And for this particular case, it's just electrons. Sometimes you'll be able to cancel out water molecules, sometimes you'll be able to cancel out protons. And then once I've canceled that out, I can rewrite my equation, and I have my final balanced equation for this redox reaction. And this is under acidic conditions. So if instead I have a basic solution, if I have a pH higher than 7, I'm actually going to approach this exactly the same way. I'm going to get to that final equation that I had, and then I'm going to make some changes. So taking that final equation, if I have a proton anywhere, I am going to replace it with a hydroxide ion. And if I have any protons and hydroxide ions on the same, or not replace, sorry, add to that side, they're going to become a water molecule. And then I'll be able to balance out my waters on each side by canceling some away. So let's look at that. So in this case, I had 14 protons on my reactant side. And so I'm going to add to that 14 hydroxides. And whatever I do to one side of the equation, I have to do to the other. So I'll add 14 hydroxides on the product side as well. So that way there has been a net change to this. Those 14 protons and 14 hydroxide ions are going to combine into 14 water molecules. And I'll represent them as that. And so now I'll be able to cancel out this water molecule on the reactant side of 14, and I have 7 on my product side. So I can completely eliminate my product water molecules and reduce that 14 to 7 on my reactant side. So I've canceled out any water molecules that were in on both sides of the reaction, and then I can rewrite this in its final form. And this is the same balanced equation. It's just now balanced in the context of a high pH solution rather than in the context of a low pH solution. All right. I'll have in the next page a practice problem to try and then a solution as well.